Alright, in this video, we study the simplest kind of linear differential equations. That is, the first order linear differential equations. So that is, we have something like this. So only the first derivative of y, and everything is linear, and possibly inhomogeneous. Okay, let's start. All right, so first let's consider the homogeneous case. That is y prime plus p of x times y equals to 0. This is a separable differential equation, so that is readily solved. So if we separate the variables, we have, so let's write like this, dy dx p of x y. By separating the variables, we have dy over y negative p of x dx. So if we integrate both sides, we have log of the absolute value of y equal to negative, this is just an integral of some function, and possibly with some constant after integrating this. So take the exponential function. We have exponential of this. Okay, but so if we get rid of this absolute value symbol, we have plus minus this. But after integrating this, there will be some constant term here, factor here. So this plus minus, negative sign, positive sign, they may be included all in this constant term. So we can just write like this. So let's see a simple example. Consider solving this equation. Okay, by separating the variables, we have, let's see, this should be y and negative 2 dx. So if we integrate, we have minus 2x plus constant. So y is equal to constant term exponential of 2x. Okay, so the plus minus arising from this absolute value is included in this constant term, so we don't have to worry about it. So this is the general solution of this first order linear differential equation. Okay, next let's consider the inhomogeneous case. That is y prime plus some function p of x times y plus some function of x, that is q of x equal to 0, where this q of x is not equal to 0. So as we have learned in the previous video, what we need to do is two things. First, find the special solution. Find a special solution. And two, find the general solution. Let's say, find the general solution of the homogeneous counterpart. So solve the homogeneous ODE. So in this case, that would be y prime plus p of x times y equal to 0. Then add the general solution of this to this special solution. Then we have the general solution of this original inhomogeneous differential equation. So the question is, we know how to solve this homogeneous case. We have just done that. So the only question here left is, how do we find this special solution given this inhomogeneous equation? One way to find a special solution is the method of variation of parameters. So variation of parameters. possibly parameters, but in many cases just one parameter. Anyway, so here how it goes. First, we solve the inhomogeneous ODE. So if we solve this equation, we have the general solution of this form. So it's some constant times exponential of something, right? So that is integral of p of x dx. Now, so this c is a constant. Next, consider this c as a variable. So that is a function of x. Okay, so let's consider a function y equals to c of x times y of x. Okay, so y of x corresponds to something like this. Okay, but c of x is some just unknown function. Okay, so now suppose this y is a solution to the original inhomogeneous differential equation. Then see what happens. So y prime, if we differentiate this by the product rule, we have c prime y plus c y prime. Okay, and using this, let's substitute this into the original inhomogeneous differential equation. So that is y prime plus p of x, y plus q of x is equal to c prime y, c y prime, and p of x, and c y plus q of x. And let's see, since y prime here, y is the solution of the homogeneous differential equation of this one. So if we just let's see, substitute, so this one and this one, let's factorize this c out, and we have c prime from here, and c, let's put q of x here, and plus c, and y prime, p of x, and y. So this uppercase y is the solution of the homogeneous differential equation. So this term should be equal to 0. So what we have left is this. Okay, and from the given inhomogeneous equation, this is supposed to be equal to 0. So left hand side, and so this should be equal to 0. Now we have a differential equation for the function c. So c prime times y, and y is a known function already. Y of x equal to 0. Now we can solve this equation for c. And that can be easily done. So c prime of x is equal to negative q of x over y of x. So if we just integrate both sides with respect to x, then we have c of x as integral of q of x over y of x dx. And that's it. So in this way, we have c of x. So y is c of x times y of x. So that is this integral times the solution of the homogeneous equation. So this should be a special solution of the inhomogeneous differential equation. Since we know the form of this uppercase y, that is this one, we can be a little bit more explicit. So that is, let's see, so this is, if we take q of x and inverse of y, that is exponential of positive, it's positive, p of x dx. Maybe we should put different variable here, x prime inside for this x prime, and an exponential of negative p of x dx. So you can use this as a formula to find a special solution for the inhomogeneous differential equation, but I do not recommend memorizing this as a formula, but instead just do this procedure every time you encounter this type of inhomogeneous differential equation. So first solve the homogeneous equation and let the constant be a function, then make this function and substitute into the inhomogeneous differential equation and solve for the function c. Then finally, we get the special solution by the product of c and y. So that's because this formula, if we call it formula, is pretty complicated. So if you try to memorize, I think it's not hard. It's not easy to memorize. And if you try to memorize and you forget part of it, and you will get the answers wrong. So instead of that, just uh, understand the procedure. Then every time you encounter the same problem, you apply the same procedure. But it's a lot easier to understand and memorize. Okay, let's see a concrete example. Let's try to solve this differential equation. Y prime plus 2y minus 3e to the power of 4x equal to 0. So this is an inhomogeneous differential equation because of this term. So first thing we do is to solve the homogeneous counterpart. So that is y prime plus 2y equal to 0. And if you get used to it, just by looking at this equation, you can immediately find the solution as this. Okay, so c is a constant. Now consider c as a function. So y prime would be c prime of x e to the power of negative 2x plus c of x times negative 2 e to the power of negative 2x. Now substitute this into this equation. So we have c prime e this and negative 2c e negative 2c and 2y plus 2 y is c e negative 2x and this one negative 3 e to the power of 4x equal to 0. So from here, this, okay, wait a minute. This and this are cancelled. So we have c prime. So multiply the inverse of this to everything, and we have c prime equal to 3 from here, e to the power of 4x plus 2x, that's 6x. So we have this. And so if we integrate this, we have 3 6x dx, that is 1 over 2 6x plus constant. Oh well, this constant is a bit confusing, so let's make it little c. Okay, this is c of x. And so just ignoring this constant term here, we can say that this is a special solution. I mean, if you multiply this with y, capital Y, then that is the special solution. So anyway, so this, so the general solution should be this thing. So 1 over 2, 6x plus constant times this. Okay, e to the power of 2x. So just expand this. We have 1 over 2 e to the power of 4x plus constant and 2x. So this is the general solution of the inhomogeneous differential equation. So this this part constitutes the special solution part of the inhomogeneous equation, and this part is the general solution of the homogeneous part. And we are done. All right, that's all for this video. See you later.